For this last talk, I'm going to discuss formal privacy as it's being implemented in some census data products. And on this first slide, I'm going to reveal my preference, I guess, for Legos over the budget metaphor. So I had the advantage of seeing Dan's slides before I prepared mine, and also I'd committed to using PowerPoint, which makes it maybe a little bit too easy to slap screenshots into the thing. But I wanted to kind of pick up on the idea that basically these tools give us an opportunity to build some pretty cool stuff. And so I'm going to discuss how these different differential privacy tools have actually been used in a few data products at the Census Bureau. So I'm going to start by talking about the Opportunity Atlas, then I'm going to move on to talk about the LEHD origin destination statistics, and then if I've got time, I'll talk about some data that I've been working on, the Innovation Measurement Initiative, which is a partnership with the Institute for Research on Innovation and Science at the University of Michigan to develop some data that are going out to universities there. But we'll see how far I get. So I want to start first by talking about the protection system that was used for the Opportunity Atlas data. This is a paper that I mentioned in the first talk by Raj Chetty and John Friedman, which describes the method that they used to get the Census Bureau to be willing to release these data. So if you're not familiar with them, these are data that provide information on social mobility outcomes for individuals who are in their 30s right now, based on the characteristics of the households that they grew up in. And what's particularly remarkable about these Opportunity Atlas data is that they allow you to look at summaries of these social mobility outcomes disaggregated by race, gender, and census tract. So census tract kind of we can think of as mapping on to roughly the level of the neighborhood. And so here's a map that's generated from the Opportunity Atlas data, which allows us to see, for instance, that Black men who grew up in Watts 30 years ago have mean household income around $7,286, whereas men who grew up in nearby Compton ended up having mean household incomes more than twice as high, around $19,000. These data are available for download for researchers to use, but they also are the background for sort of mapping application where you can plug in, say, so I could plug in my neighborhood here in Athens, Georgia, and then it'll tell me that children that grew up in households in this neighborhood, say 30 years ago, ended up making around $43,000, here focusing on white males. And I can get these estimates not only separated by tract, but for looking at households where household incomes were either low at the 25th percentile, at the median, or high incomes. Okay, so these are remarkably rich data. And so the question is, how exactly did they persuade the Census Bureau to let them get these data out the door? Because I'm not aware of any other data that provide quite this rich a detail on individual outcomes at quite this high level of geographic resolution. And so it was possible by using the formal privacy system. So the Opportunity Atlas data are based on tax records, but we can sort of think about the raw data a little bit more abstractly. So we've got data for individuals I, who are in some race, gender group, and who grew up in a particular census tract. So we'll think about all of that as being a group G. And these groups G partition all of the data. All right, so every individual in the data is going to fall into exactly one of these groups. And for those individuals, for that group, we have a database that tells us a set of social mobility outcomes that we're interested in. So for instance, your income rank as adulthood, and they give you information on the income rank of the household that you grew up in, the income rank of your parents. So what they do with these data is fit least squares regression models. This is a little bit of a simplification, but not much of one. Fit least square regression models, one for every group. So the data are completely disaggregated. So we're fitting a regression for each group where I'm going to predict the outcome that I'm interested in as a function of the household income rank. And then the queries that they're interested, the things that they're publishing, the things that they want to get out and put into the Opportunity Atlas are essentially just predicted values at each income rank, in particular the 25th percentile, the 50th, and the 75th. Okay, so those are the queries of interest. And now here's the issue. These are very small cells. And once we get down to the tract level, the population is small to begin with, and we're disaggregating by race and gender. And these predictions, these predicted values, have potentially high sensitivity. Okay, so nevertheless, the basic idea, the basic building block here is to think about calibrating the noise to sensitivity. And so what you could try to do is to publish the statistic that you're interested in by essentially taking the true statistic and adding some Laplace distributed noise, where the noise is scaled according to the sensitivity of the statistic that we're interested in. Here are these predicted values. So if you do that, we know from Dan's talk that this is going to satisfy epsilon differential privacy. And because the groups partition the data, we're going to get a parallel composition results that tells us that we can actually publish these for many, many different groups, but actually at a relatively low level of privacy loss. This isn't going to work though. So recall that differential privacy depends on how much the output can change when it's evaluated on any two different data sets, right? So the problem is that when we're thinking about this global sensitivity calculation, we have to think of all of the potential inputs that could be fed in, not just the ones that we observe. So global sensitivity here is just too high. For the opportunity atlas, again, the sensitivity is how much the conditional mean of, say, the child's rank and the earnings distribution could change if you add or remove any legal value from any conceivable data set. And the answer is a lot. So they show this hypothetical example of a case where we have a particular group where there's not very much variation in the parent's income rank. And so if we add an outlier, say somebody who grew up in the poorest household possible and ended up being in the highest income rank, then that's going to cause the slope and all of the predicted values to change considerably. Okay, so our sensitivity is going to be high if we focus on the global sensitivity. Okay, well, so that's not going to work. So what else might we try? Well, we could think about using something called local sensitivity. So global requirement is overkill. Because in this case, we know we have access to the data already, and we're going to apply this method to this particular data set. So we don't need to think about all of the potential data sets that we have. We need to think about protecting deviations from the data set that we actually have. So this gives us the concept of local sensitivity. How much could the conditional mean of child earnings rank change if I remove or add any legal value from the observed data set? The answer there is not as much. So if I look at the regression in the data that I actually have, this is the same sort of issue that comes up in general when we're thinking about sensitivity of regression estimates. Most of the time, we don't expect our regression to be particularly sensitive to an outlier, but it's only in these extreme cases where we get high global sensitivity results. Okay, so this seems pretty promising. And so this suggests a new method where we could just publish the true prediction plus some Laplace distributed noise, where the variance of the Laplace noise is now scaled according to the local sensitivity. The problem with this thing is it's no longer going to satisfy epsilon differential privacy for reasons that Dan alluded to in the talk that he just gave. This is frustrating. So this privacy aware analysis requires that not just that we publish the query results that we're interested in, the predicted values plus the noise, but to do the privacy aware analysis, we also need to publish information about the variance of the noise distribution. And in this case, the variance of the noise distribution is based on local sensitivity, which is a function of the true data set. So that makes it also a population statistic. And that means that it also has a privacy cost. So we can't publish the local sensitivity without adding to the privacy cost. So a third approach, and this is the innovation in this Chetty-Friedman method, is to think about constructing an upper bound on the local sensitivity that is not disclosive of the information in each cell, but that is does not require adding quite as much noise as the global sensitivity. And so the way that this works is you could just calibrate it to sort of the maximum observed sensitivity that you ever see in any cell. So this is a plot of the sensitivity of the 25th percentile predictions per household against the number of individuals in a tract, both plotted on a log scale. So what you see is that the sensitivity tends to be higher in tracts that have small populations and decreases linearly in the logarithms as the population increases. And so you could calibrate the noise according to the maximum observed sensitivity, which would put it at this level. That turns out to also add too much noise, and so instead they calibrate relative to the scaling parameter deflated by the population size. So the sensitivity is going to now be a function just of the size or the number of individuals in each group. Okay, and so this is a Goldilocks solution. So you can use the Laplace mechanism, publish the true query plus Laplace distributed noise, where the Laplace distribution is scaled according to this maximum observed sensitivity envelope. It's now a function of the size of the cell, and where the scaling parameter is constructed by just taking the maximum over all groups of the product of the number of individuals in the group and the local sensitivity of that group. So this, unfortunately, is not epsilon differentially private, because technically, when we're publishing this scaling parameter, it is a function of the data, and it is published in a non-distorted fashion to be able to adjust inference. But however, if we're willing to condition on the existence of this scaling parameter, then the publications for the Opportunity Atlas satisfy the differential privacy guarantee and satisfy parallel composition across the groups. There's some further implementation details, but I'll skip through these. One interesting note, though, is that according to the paper, they set the privacy loss parameter at epsilon 8 and argue that this is based on, they based on an accuracy measure that was framed in terms of the probability of correctly classifying tracks in either the top or bottom tail in terms of social mobility measures. But they don't get as far into the details of exactly how that process worked as I would like. But this is exactly the problem that is kind of at the heart of the first part of my talk. And so thinking about how more information about how these privacy loss parameters get set, I think, is important to be discussed. So takeaways from this first application, this MOSE hack, maximum observed sensitivity envelope hack, solves the issue of high global sensitivity. It's hard to imagine these data being published under a conventional statistical disclosure limitation. And as I showed in the first talk, if they had been allowed to do it through self-suppression, it would give far worse inferences. And of course, we'd not be able to do privacy-aware analysis in the same way. There's new research actually published in an archive just this month that gives full differential privacy results for this class of problems. And so there's progress currently being made on this sort of problem. Okay. So now I want to pivot to talking about a different type of formal privacy model applied to publication of summaries of linked employer-employee data. And so this is a paper by Haney, Vahala, John Abad, Graham, Kutzbach, and Lars Wilhuber. So the question here is, how do you protect the data that are known as LODES? So the LODES are the LEHD origin destination employment statistics. And the data that underlie the LODES are essentially a tabulation of jobs that are in the LEHD database. So these are jobs that are subject to unemployment insurance taxation. And they include information on the characteristics of the workplace, including its location, the industry, and the type of ownership, and characteristics of the workers, including their residential location, age, race, ethnicity, and gender. And so these data can be used to track commuting patterns as well as to understand kind of the distribution of employment by different demographic characteristics across space. So once again, the data here are sparse because of course we're looking at employers, geolocated down to the block level. The employment data can be right skewed, and so that means that there's the potential for a lot of disclosure of employer characteristics. Furthermore, there's a statutory requirement to protect both the workers and the employers. And so this kind of calls into question what exactly is the nature of the underlying database? And how exactly should we think about neighbors? Should we think about neighbors as neighboring databases as being one where I add or remove a worker, or one where I add or remove an employer, or something different? And it turns out that it's something different. So there's an approach that they introduce in this paper that's based on privacy protection notion called pufferfish. And the basic idea is that first decide what needs to be protected, and then define neighboring databases in terms of those protected characteristics, and then devise provably private algorithms on the basis of that. Essentially what's going to happen is through the application of sort of a clever definition of neighboring databases, you can apply most of the differential privacy technology to this problem in a way that deals with the high sensitivity of the data. The first question, and this is an important one to start asking if you're end up in the situation of designing one of these things, what exactly is it that needs to be protected? Because you don't want to add more noise than you need to protect things that don't necessarily need to be protected. So they argue first that based on statutory requirements, the data need to satisfy the condition that there's no potential for re-identification of individuals. In particular, it shouldn't be possible to learn too much about whether or not a particular individual was in the database or not, whether they work for a specific type of employer, whether they have a particular set of demographic characteristics. So this is the same type of privacy guarantee we've been thinking about all along. However, for employer establishments, the situation is different. The privacy requirement there is that we only need to protect against precise inference of establishment size. So in particular, the fact that an establishment, an employer business exists is not considered to be private. The industry and location where that employer business operates are also not considered to be private. And finally, the course size is private, just not the exact size. So in other words, we need to protect against the ability of an adversary to learn about an exact establishment size, but it's okay if they learn some information about the fact that, say, the employer is large or small. Finally, there shouldn't be an ability to sort of make precise inferences about workforce composition. So that is, it shouldn't be possible to infer things like the share of workers that are female in a particular establishment. So I'm going to focus on points 1 and 2. Point 3 involves more technical detail than I'm inclined to get into. Okay, so there's a sort of formalization here, which is to try to think about exactly who are we trying to protect, who are we trying to protect the data from. And so here they introduce the concept of an adversary. So in this setting, we're going to imagine an adversary who knows the set of all employer establishments, E, and their public attributes. And they know the set of all workers that could appear in the database, but they don't know which ones are in the database. And for each worker who could be appearing, they have private attributes. But again, the adversary doesn't know what those private attributes are. And one of those private attributes is where they work and whether or not they appear in the data at all. So the adversary is potentially trying to learn all of these characteristics. The adversary has beliefs that consist of a distribution over the worker's attributes, right? And then those can just be composed together to give prior beliefs about all of the workers that might appear in the data. Okay, and on the basis of this adversary concept, they define two concepts I'm going to discuss. One is an employee privacy requirement, and the second is an employer privacy requirement. So employee privacy requirement just says that on the basis of the published data, it should not be possible for the adversary to update the log of the base factor by more than a factor of epsilon in differentiating between whether a worker had characteristics, say, A or B. So it's going to, so this is the privacy guarantee, or the requirement that any mechanism should satisfy to satisfy the privacy requirement. Employers get a guarantee of protection of the employer size. And here, they add the concept of an additional privacy parameter, alpha. And so alpha is a parameter that's going to make precise exactly how fine-grained the attacker's inferences about the employer size can be. So what this is saying is that the employer size requirement says that an attacker's posterior inference about whether the employer has size X or has size 1 plus alpha X is going to be bounded by a factor epsilon. So this is telling me that the privacy requirement is specifically that I'm going to shield employers against an attacker's ability to learn whether or not their size is within a factor of alpha from its true value. Okay, so to operationalize this, we need a new concept of neighboring databases. So the first option would be, we could think about neighboring databases as being ones where we add or remove a single worker or a single employee. In that case, all of our queries in this context are counts, and so we could be operating the Laplace mechanism with sensitivity 1, but if we do that, then we're going to fail to satisfy the employer size requirement. Option 2, we could just think about adding or removing an entire employer as being the neighboring database concept. And that would mean that the sensitivity of any calculation would basically be bounded by the maximum size of any employer in the database. And so our queries could include the sums of all workers. This would satisfy all of the requirements, all of the privacy requirements, but it's going to give us atrocious data quality because the sensitivity would be too high. So once again, there's a Goldilocks solution, and that's to construct a definition of neighbors, which they call strong alpha neighbors. So we're going to say two databases, D and D prime, are strong alpha neighbors if they differ in the employment attribute of exactly one employer record, E. And if we let X be the number of workers at E, so this is the size of the employer establishment in the initial database D, and X prime is the number of workers in establishment E in the neighboring database D prime, we just require that the number of workers in the neighboring database be bounded between the initial level X and 1 plus alpha times X. So in other words, neighboring databases are going to be those where I take a single employer and replace their employment with a value that could be up to 1 plus alpha times its value. So this leads to a new privacy concept, which is alpha epsilon EREE privacy. And so here, but the privacy definition is exactly the same privacy definition that we saw for differential privacy. All that we've changed is our definition of neighbors. So now we're saying that for every pair of strong alpha neighboring databases, the ratio of the probability of seeing any output when the mechanism is operated on the data set D relative to its strong alpha neighbor D prime is going to be bounded by e to the epsilon. So this is sufficient for worker and establishment size requirements, and it's going to inherit all of the nice composition properties that we get from the standard differential privacy results. So the trick here is essentially to just define the neighboring databases in terms of exactly the quantities that need to be protected. Now in application, the global sensitivity here can still be high. So the key query is total employment. So if Q of D is such a counting query, then the L1 sensitivity would still be the difference between operating that counting query on the initial database and implementing it on its strong alpha neighbor, the sensitivity can be as high as the maximum over all employers of alpha times alpha times the level of employment. So if employment can potentially be very large, then this sensitivity can still be alpha times something very large. So this could still give problems with sensitivity, at least global sensitivity. So global sensitivity here is essentially unbounded. However, if instead you look at the sensitivity of the log of the counts, that's going to be bounded by 1 plus alpha. And so they build a mechanism called log Laplace, which essentially just takes, which adds noise to the log of the count and then takes an exponential to back out the, to get the published count. Log Laplace mechanism satisfies strong alpha epsilon privacy for employer attributes, but does have the result that it's biased. However, through post-processing, you can correct for the bias that's introduced by taking these logarithms. They also introduced some other mechanisms using an approach called smooth sensitivity, and this is a complementary approach to the Goldilocks problem. So here, the idea is kind of like in the Chetty-Friedman case, you want to find some bound on local sensitivity and use that as the noise scaling factor in operating, say, the Laplace mechanism. So the idea is to derive a function, S, it's a function of the data such that that function is always above the local sensitivity, like in the maximum observed sensitivity envelope, but it satisfies the property that that function is itself not particularly sensitive. So if I operate this function on the initial database versus any one of its neighbors, it's going to be bounded above by a factor e to the alpha. So what this means is that operating with the smooth sensitivity in this particular use case, you can add noise that's proportional to the maximum of alpha times the employer size over just the set of employers that are in the initial data set. And on the basis of that, they generate two additional algorithms, one called smooth gamma, which basically adds gamma distributed noise calibrated to this local, or calibrated to this smooth sensitivity, which is unbiased, and a smooth Laplace, which satisfies an approximate privacy guarantee and is also unbiased. So something I like about this paper is that they compare the effects of this form of privacy protection with the existing privacy protection mechanisms. And so they're looking at the L1 error on a set of counts, which are margins across all different places, census places, NAICS sectors, and ownership categories. And compare the L1 error using the original system relative to the proposed system. So when this L1 error ratio is above 1, it means that the proposed mechanisms, these formally private mechanisms, are doing worse than the preceding mechanism. And when it falls below 1, they're performing better. So what we see is that the log Laplace and smooth gamma, so we have epsilon on the horizontal axis, and each of the lines here corresponds to different settings for alpha. So as alpha changes, we're changing what it is that we're providing a privacy guarantee of. So say when alpha is set equal to 0.2, we're telling employers that it's not going to be possible for an adversary to learn their true employment to within a factor of 20%. Whereas if alpha is equal to 0.01, we're telling employers that it will be impossible for an adversary to learn their employment to within a factor of plus or minus 1%. So those are very different promises. The factor epsilon tells us exactly how much they're likely to lose. It tells us about the probability how much an attacker is going to be able to learn about whether or not their employment is within, say, for the factor of alpha. So what we see is that we need to, if we set the factor of alpha relatively low, then we're providing a relatively weak guarantee of privacy, but we can get acceptable quality. However, as the degree of coarseness with which we're willing to allow adversaries to make inference increases, the quality deteriorates, and you need a greater degree of privacy loss, a greater epsilon, to sort of counterbalance that. So there's a trade-off here between alpha and epsilon. The smooth Laplace, because it's an approximate method, tends to do better on all of these different measures. To wrap up, I'll spend some time talking about work that I've been doing at the Census Bureau with the UMETRICS. So this is the partnership between the Institute for Research and Innovation in Science, IRIS, and the Census Bureau. And the goal of this partnership is to track employment and earnings outcomes for grant-funded employees. There's more research going on here in the Innovation Measurement Initiative. This particular data product is something called an employee profile report. The idea is to report back to university partners information about the employment outcomes for individuals who were funded on grants who attended those institutions. So IRIS is receiving data from different university partners that provide information on individuals that were funded through grants and vendors that were supported with grant funding. And they want to, and the partnership links data on the outcomes for individuals that come from W-2 records, information in the LAHD program, and in the business register. So the desired outputs here is the IRIS wants to be able to report to its university partners characteristics of workers. So in particular, employment outcomes and average wages disaggregated by an individual's title when they were at the university, so whether they were a faculty member or grad student, their sector of employment after leaving the university, so whether or not they ended up in academic environment or non-academic environment. And they want to track those outcomes for up to 10 years after leaving the university. And furthermore, there's one table for each university. So privacy requirements here are to protect the university employees against re-identification on the basis of whether or not they're included in the data at all, and all of the attributes of their employment history. So that means that neighboring databases are going to be those that add or remove a single employee and their entire employment history. I'll just note that this would be a simpler problem if all we were worried about was just protecting a single job. So if it were, say, for instance, okay to know that an individual worked for the university, we just don't want to disclose too much information about their earnings or employment in any single year, and this problem would be different. So the methods that we use to do this publication, first take the Laplace mechanism to generate the employment counts, which have sensitivity 1. We used a modified version of the maximum observed sensitivity envelope to be able to publish the average earnings using the Chetty-Friedman method, where we calculate the maximum observed sensitivity scaling factor at a job title by sector level. And this places an upper bound on our and another upper bound on the sensitivity envelope. And something that made this implementation a little bit different is that we have an accuracy requirement due to pre-existing agreements with IRIS. They had an expectation of a threshold level of data accuracy measured in terms of an average % deviation. So that is on average, the difference between the true and noisy values scaled by the truth need to match some preset level. Okay, the thing I want to focus on here is the privacy analysis, where we want to understand, after we do all of these calculations, what's the total privacy loss? So you can reason through the different composition possibilities. So each worker appears only in one job title by sector pair. And so that means that across those groupings, we can do parallel composition. However, each worker can appear in multiple years of the data. And so that means that every time we're publishing, say, information 1 year out versus 2 years out, those privacy losses have to be accounted for using serial composition. And finally, each record is used both to compute total employment, the employment count, and the earnings level. So we once again have serial composition. So if we define epsilon of epsilon imp ts, so this is the privacy loss parameter for employment queries, t years after leaving university S, and the second privacy loss parameter for the average earnings queries, t years out after leaving university S, then the total privacy loss associated with publishing this employee report is going to be the sum over all years, say 1 up to 10, because of the serial composition result of the privacy loss associated with publishing employment for that cell and the privacy loss associated with publishing earnings for that cell. Because if we set this privacy loss parameter the same for each job title by sector group, parallel composition tells us that the total privacy loss is still just epsilon s. So this is our total privacy loss associated with publishing the data for a single university. Something to highlight then in thinking about these privacy losses is that this means that universities that are particularly small or have fewer years of data end up with a different allocation of the privacy budget than universities that have many years of data or have much larger cells. So the distortions that are introduced by this process are reduce the quality more for small universities than for larger universities. And so ideally, these privacy losses could be tailored to individual universities. Other examples that I won't go into of formal privacy systems being used at the Census Bureau are the data in the post-secondary employment outcomes, where there's a clever method for publishing the entire distribution of earnings for individuals after completing university education and the veterans' employment outcomes. You can read up on the documentation for these methods in this paper, which is linked here, and the slides that will be available on the website after this talk.